Welcome to a brief overview of sounding rockets. Sounding rockets take their name from the nautical term to sound, which means to take measurements. Since 1959, NASA-sponsored space and Earth science research has used sounding rockets to test instruments used on satellites and spacecraft, and to provide information about the sun, stars, galaxies, and the Earth's atmosphere and radiation. Using sounding rockets is a simple, cost-effective, and time-efficient way of doing research without the long lead time and expense needed for the launch of an orbital rocket. The rockets are divided into two parts: the payload and a solid-fueled rocket motor. Many of the motors used are surplus military motors. After the launch, as the rocket motor uses its fuel, it separates from the payload and falls back to Earth. Meanwhile, the payload continues into space and begins conducting the experiment. In most cases, after the payload has re-entered the atmosphere, it is brought down to Earth by way of a parachute and is then retrieved. By recovering parts of the payload, it can be refurbished and flown again, resulting in further savings. Scientific payloads are carried to altitudes from 30 miles to more than 800 miles. And although the overall time in space is short, typically 5 to 20 minutes, the experiment is perfectly positioned to carry out its mission successfully. Collected data is often returned to Earth by telemetry links, which transfer the data from the payload directly to the researchers on the ground. Let's hear a little bit about how that works.
This is essentially the hub or main network of the entire payload. The experiment is collecting its data. That data then gets passed through to this structure. The structure processes it, encodes it, sends it to the ground. This is our control rack. So when we're in the blockhouse counting down, this is what we use to control the payload. So when we have the umbilicals plugged in, this is what's controlling it. This setup here.
Of course, if you're going to launch a rocket, you're going to want it to fly as efficiently as possible.
This bay right here is the balance bay. Since our rockets are spun stabilized, we want them to spin about their geometric center axis. The principal axis is what it's trying to spin about. And if anyone's seen someone driving down the road and their tire's bouncing, that tire is trying to spin about a principal axis that's not in the middle of the tire. So you balance your tires. Well, we balance our payloads the same way, essentially. We use two planes though, so we'll balance in two separate areas. There's two types of imbalance, there's static and dynamic. And we can capture both those imbalances. Static imbalance is where the principal axis is not on the center of geometry. And then you've got the dynamic imbalance, which is where that principal axis is trying to lay over. And we can measure how much it wants to lay over. And the thing that you get when you have a spinning body and it's trying to lay over is you get coning. And that coning causes a lot of energy loss. So you don't fly as high, you don't go as far. And for sounding rockets, especially with telescopes, the higher the better. Those guys want to stay up as long as they can.
Of course, a rocket launch is a pretty violent event. One has to be sure that the instruments and general construction of any experiment launched will survive the trip.
Here, these are our shaker tables. We use them to simulate the vibration environment the payload will experience during flight. We actually vibrate it to 125% of the maximum flight environment, and that is done because we can pretty much guarantee if it survived our vibe test, it's going to survive flight. That's really how we're able to pump out 24 rockets a year and still maintain a quality product, is doing these tests at that level. These are basically giant speakers. They have a wire coil in the middle of them and a magnetic element that moves. As a matter of fact, when they installed them back in the 60s, they played Christmas music over them using a cassette deck. The cool thing about the wire coil though for here is they actually have coolant that runs through it. So it's actually copper tubing with a coolant that runs through it because these things get pretty hot.
Another metric of interest to ensure a successful mission is payload flex. Let's hear a little about that.
Okay, so another test that we do is we do a static loads test. The mechanical engineer predicts how flexible the payload's going to be and sends that to flight performance. Flight performance then creates a model using that flexibility, and then they run simulations, and we get statistics from that. We get a statistical dispersion from that. And in order to verify that that model is conservative and that it's true, we will bolt the payload to the floor and actually push on it with that pneumatic piston up to the maximum bending moment of the flight, and we measure the tip deflection. And what we do with that is, if the payload is under deflecting, flight performance's model is conservative, everybody's happy. It's definitely worst case scenario.
It's also kind of handy to know how easy or difficult it's going to be to control or reorient the payload.
So the mass properties table measures center of gravity, moments of inertia. We measure the moments of inertia in both pitch, where the rocket is actually laying across the table, and we measure the moment of inertia this way, and we measure the moment of inertia in roll. And the reason we measure those, it's good to know how hard it's going to be to move this body in space. So we use that to determine attitude control, how big do the nozzles need to be, what gas are we using, things like that. And we do it in roll because a lot of our rockets, even though it's spinning while it's flying, it does not want to be spinning at 4 hertz when it gets exo-atmospheric for the science portion. So we can put what we call yo-yo D-spin cables on the side of the rocket, which is literally 2 brass weights. We fire a pyro that releases the brass weights. The brass weights are attached to 2 cables that are wrapped around the rocket. So as the rocket's spinning, the cables are flying away and it's absorbing all the rotational energy from the payload. And that literally happens in a fraction of a second. Pyro will fire and boom, it's despun to 0 or 1/4 hertz.
The use of sounding rockets for tests can have far-reaching results. All the way to Mars, in fact, as in Mars 2020.
So we just launched a series of rockets from Wallops that were for Mars 2020. We were testing the supersonic parachutes they needed to decelerate the lander. So one of the things about trying to get people on Mars is you've got to get bigger. Bigger things are going to have to land. Well, one of the problems they were having was slowing these bigger things down with such a thin atmosphere. Well, with our platform, with the sounding rocket, we're able to actually get up past the Earth's atmosphere into an atmospheric density that is similar to Mars. So we actually designed, built a rocket with JPL to launch their parachute so that they could test the whole re-entry vehicle.
At 6:45 a.m. on October 4th, NASA performed its first supersonic parachute test in support of its upcoming Mars 2020 mission.
3, 2, 1.
The 58-foot-tall sounding rocket launches off the eastern shore of Virginia out of NASA's Wallops flight facility. This 2-stage rocket accelerates to over 3 times the speed of sound at an altitude of over 50 kilometers, or nearly halfway to the edge of space. Once the second stage has burned out, it separates from the payload and the payload continues to the desired test condition. On board is a new payload designed to test parachutes in a low-density environment and at supersonic conditions analogous to what NASA's Mars 2020 mission, America's next Mars rover, would encounter as it comes through the Martian atmosphere. As the payload dives back into the atmosphere, the roar of the oncoming wind becomes more audible. Onboard computers detect that it has achieved the proper test conditions and subsequently deploy the parachute. 100 pounds of nylon, Technora, and Kevlar are shot out of the back of the vehicle at nearly 100 miles an hour. In slow motion, and video originally shot at 1,000 frames per second, but played back here at 30 frames per second, we see the initial suspension lines deploying out of the pack and taking the parachute backwards, where it will ultimately inflate in nearly half a second. Researchers watching this video are observing the initial motions of the fabric, the uniformity of the inflation, and how symmetric it is, and they began inferring which areas may be more structurally loaded or stressed than other areas of the parachute. Every frame will be examined closely to look for signs of damage in any of the stitching used to hold the canopy together. At the moment of full inflation, the parachute is going 1.8 times the speed of sound, or nearly 1,300 miles an hour, and generating nearly 35,000 pounds of drag force, drag that would be necessary to help slow a payload down as it was entering the Martian atmosphere. This was the first of several tests in support of NASA's Mars 2020 mission. The data obtained during these tests are critical for better understanding the environment and dynamics of a supersonic parachute inflation at Mars.
Well, there you have it. I hope you've learned a thing or two about sounding rockets, how they're made ready for launch, and why they're an important part of the United States space program. Thank you all very much for watching, and I'll see you next time.